Let's move into section 5.4, which talks about the indefinite integral. Now, what makes this an indefinite integral as opposed to what we had just a minute ago, where we had stuff like this? When you have the limits, that's a definite integral. If you don't have limits, then it's an indefinite integral. Basically, the indefinite integral for us is going to be the same thing we did in section 4.9, finding antiderivatives. So, when you're asked to find the antiderivative, don't forget you want to include that constant of integration. That becomes important. Then you need to find an antiderivative of something like this. This is kind of like a Calc 2 problem, so for those of you headed towards that to that fun, that's going to be something you're going to face this fall, hopefully with me. In any case, they say that this is true, and they say to check by differentiation. How would you check it by differentiation? What would you have to do? What would be true if this is correct? Yeah, take the derivative of it, and what should I see if I take the derivative of it? The integrand, right? So this function that's inside your integral is called the integrand. So, one of the things I learned in college was Spanish, and I like learning different languages and things like that. And I was curious, well, what do you call this? What's the great Spanish word for this? And it's integrando. I'm like, okay, that's not really cool. I wanted some really weighty term, something like meatballs in Spanish is albóndigas, which is kind of like a nice juicy word, but yeah, integrando. Kind of disappointing. But yeah, if you differentiate this, and it's not something I feel like taking the time to do right now, you should get this. Just a quick FYI, if you were to differentiate this, I'd probably write it as 7 times 1 plus x squared to the 1/2. And then you can multiply it by x to the negative first. I'd probably use the chain rule here. Not the chain rule, but the quotient rule. Just because if you use the product rule, then you're going to have to get common denominators to get it all to work out nice. And it's just not going to be as easy a process. So suck it up and use the quotient rule on that one. But let's start our work with example B and C here. So example B is going to look like this. The integral of u plus 6 times 4u plus 9. And although differentiation and integration are opposite operations, they don't always have opposite properties and theorems. For instance, there's a product rule for differentiation, but there's no product rule for integration. You can't say that, oh, that's the integral of u plus 6 times the integral of 4u plus 9. It just doesn't work. Sorry, there isn't anything like that. So, as tempting as that might be, please avoid it. You can't do it. I got to come up with a nice abbreviation because I get weary of writing can't do it this way on exams. People try. It'd be nice if there was a product rule like this for integration, but there's not. So what else could I do to find an antiderivative here? Any suggestions? Yeah, you can multiply it out. You can FOIL it. So let's FOIL it. Let's just do part of this in our heads. That's going to be a 4u squared plus 9u plus 24u is going to be plus 33u plus 54. And all of that is du. Please do keep that differential term around. It is something that I'd like to see. It does make a difference. There are places where you're going to need it, mostly in Calc 2, but I do want to see it. So now we can find the antiderivative of this. So let's see about that. Let's do it term by term. Add 1 to the exponent, divide by that same exponent. It's going to give you 4u to the 3 over 3. How about the middle term? What do we got going there? Thank you, Rihanna. 33u squared divided by 2. James? Next one? Antiderivative of that term?
54u.
54u. Nice. And Jameson, what am I forgetting?
Plus C.
Well done. Thank you both. Plus C. Bam. We're done.
That was easy.
Yeah, pretty nice. Should give you a dozen problems like that on the exam, right? Let's keep going. They're not all going to be that easy, so where are the tougher ones? Well, let's start with one that I did one like this the other day. I'm doing one like this again today, which is kind of like a subtle signal to you. Yeah, watch out for something like this. Again, there's no quotient rule for integrals. I can't integrate the numerator divided by the integral of the denominator. It just doesn't work. So what are my alternatives? What could I do? All right, let's split it up as 5 over x plus x to the 1/2 over x plus x over x, all that dx. And let's see here. I'm just going to leave that first one as 5 times 1 over x. How about the second one? How could I rewrite that? Any suggestions? X to the negative 1/2. Remember, these things subtract. X to the negative 1/2. Keegan, let me give you an easy one. How about the last one? Is there a way I could rewrite that one?
1.
Yeah, 1. Nice. So the antiderivative of a couple of these isn't too bad, but how about that first one? What am I going to do with that first one? Let me give you a hint. It's going to be 5 times something. Ooh, well done, Ethan. Bravo. Made that look easy. ln. Remember, the antiderivative of 1 over x is going to be the natural log of x. Great deal. Now, for this one, you're going to add 1 to the exponent. What's negative 1/2 plus 1? 1/2. And you're going to divide by that same exponent. Laura, I need an antiderivative of 1.
X.
Yeah, x. Nice. Mage, what else am I missing? Plus C. Thank you. That plus C is going to become later for us, useful for us in example K. But it's going to be ways before we get there. Let's clean this up just a little bit. I'd be unhappy if I left it as x to the 1/2 divided by 1/2. Divided by 1/2 is the same thing as multiplying by what? 2. So it's going to be plus 2x to the 1/2 plus x plus c. That's your final answer. So, yay. Looking good on that one. All right. Arlie, if I was looking at that and feeling a little uneasy and I wanted to check it, how could I check it? Yeah, take the derivative, and I should get back to this thing here, which is this, which is this. Yes, so yeah, eventually you could get back to the original integrand. So yeah, well done. It's kind of nice that you can check these things. I think math is kind of unique in that. It's not too many classes where you can actually check your answers before you hand in the exam, right? But you can in math. Take advantage of that. Let's take a look at C here. No, that was C. All right. Now let me just put that in here. So example C. Let's move on to D. So example D. This time I've got the integral of, and I'm going to call an audible here. I'm going to write that with a y as opposed to a t. I just don't like t's. Secant of y times 5 secant of y plus 9 tangent of y dy. Okay. Well, you know, again, we're kind of stuck with the fact that there's no product rule for integrals. I can't integrate this and then integrate what's inside here. So suggestions. What do you got? What can we do here? All right, let's distribute the secant of y. So, Antonio, when I distribute the secant of y, what do I get? Good. All right, I'm going to write it in the other order, but it's the same thing. Thank you so much. Okay, now when you're finding the antiderivative, you can kind of ignore the constants a little bit. They don't go away, but you're just not really going to focus on that part of it. You're going to look at something and say, all right, well, what do I differentiate to get secant squared? Iris? Does that one come to mind? What do you differentiate to get a secant squared? Tangent. Thank you, sir. Thank you, Iris. 5 secant squared becomes 5 tangent. How about secant tangent? What do I differentiate to get that? Just secant. And then what else do I need to finish this up? Oh, let's forget the 9 there. Plus c. And then there we go. That's it. All set with that one. Looking good. Looking good. Let's keep rolling. Looks like you have that problem twice, right? Yay. So that's good news. We're done with part E. I guess, yeah, that's not part E. I guess this is example E. Let's move on to example E. My screen's been drinking. There we go. So it says graph several members of the function of curves for different values of c. So let's first of all find the antiderivative of this. And you have to think a little bit to find that one. So I'll give you a second. See if you can't find the antiderivative of that. And while you're working on that, let me pull up a link. Let's see, right here. Okay. What do we got here? Lucas, I need some antiderivatives. Start with the cosine.
Sine x.
Good. Sine x.
Yeah, I haven't got the other one yet.
We'll tell you what. Let's do it together. The 1/9 we'll just kind of leave there. What's the antiderivative of x squared?
Antiderivative of x squared.
Yeah, or excuse me, antiderivative of x. I guess I kind of get away a little bit.
X squared. Or
X squared over 2 plus our constant. So we can rewrite that as sine of x plus 1 over 18 times x squared plus a constant. And what they're asking you to do is graph this for several different values of the constant. So we can do that. It's probably easiest done in Desmos. I did it kind of creatively this way, but one way or another. So what you're seeing are different levels of this function. They all have the same derivative, right? The slope of the tangent line is going to be the same no matter where you're at. It's just shifted up vertically or down vertically depending on the value of c. But there you go. There's your 5 different values of c. So cool. Looks good. Looks good. All right. Let's move on. we're going to go back to interpreting the function, or excuse me, the integral as actually an area. And typically speaking, what we do is we think of the area as being between the curve and the x-axis. So we saw that with this example, example F from section 5.3. That is, the value of this integral is really just the area between this curve and the x-axis. So right now, when I'm letting the upper limit be 0, then it's just the area between -2 and 0 of the function. Let's see, the function is actually 2 right here. So that area is just going to be the area of this rectangle, 2 times 2, which is 4. But as I move to the right, now it's going to start picking up the area between the parabola and the x-axis. So it's going to increase that area. So looking good there. We're going to have to do the same thing with some of these other curves, except there's a little difference here. This curve is butted up to the y-axis, but that doesn't mean we can't write an expression to find the area. So what's that expression going to be? Well, let's see here. We're going to do this with respect to y as opposed to with respect to x. So let's take a look at the limits here. Where are we looking at the area between? Well, the lower limit is going to be 0, the upper limit is going to be 4. And if I wanted to try and find, say, for instance, the area by a Riemann sum kind of approach, like we did back in section 5.2, so this kind of approach where you allow, let's see, more and more rectangles, these, etc., more and more rectangles, then let's start out by finding the area of one rectangle. So I'm going to draw a little rectangle in here. And because I'm slicing this region with respect to the y-axis, I'm going to call that distance, or the height of this little rectangle, I'm going to call it dy. Maybe you want to think of it as the width, that's fine. But then I need this other direction. What's the length of this in this direction? That'd be dx if we did a vertical slice. It's just going to be the value of the function at that point, which is going to be 4y. So this is going to have coordinates of x and 4y minus y cubed. But in particular, because this is in units of y, I want this in units of y. So the area of this one slice,
Yeah.
is that a y squared? My bad. Thank you. The area of one slice is going to be this height, 4y minus y squared times dy. Now that's just the area of one slice. But I want the area of all such slices. So to get that, I'm going to put this in an integral. 4y minus y squared dy. And that's the integral that you would use to find the area of this little piece of a parabola between the parabola and the x-axis or the y-axis. Now, as far as evaluating it, let's go back and finish the evaluation part. Let's see. New sheet here. So this is still example F. We've got the integral from 0 to 4 of 4y minus y squared dy. Start by finding an antiderivative. What's the antiderivative of 4y minus y squared? Well, you don't have to get it perfect right away. Let's just start this way. Add 1 to the exponent, so it's going to be a 4y squared divided by 2. Add 1 to the exponent, divide by the same exponent. Same thing over here with your y squared. Antiderivative of that, add 1 to the exponent, divide by the same exponent. Put a straight line here because we've already found the antiderivative. Now it's just a matter of evaluating this function at those two endpoints. It's up to you if you want to clean this up a little bit. Maybe we will. That's 2y squared minus 1/3 y cubed between 0 and 4. Put in the top limit. So it's going to be 2 times 4 squared minus 1/3 times 4 cubed minus, well, let's just put in a 0 there, right? Because each of those terms is going to turn to a 0. So it's going to be 32 minus 64 over 3, which I think is going to be 32 over 3. Usually Katie checks me on those things. Yes. Good deal. Thank you. Nice. Nice. Let's try example F. In fact, I'm going to let you try example F. So that's this one. And I believe that's y equals 4 times the 4th root of x. So see if you can't do kind of the same thing that we did just a minute ago. Maybe draw yourself a little rectangle. Now this little piece here is going to be one side of your rectangle. It's going to have dimensions or length of dy. See if you can't put together a little expression to find the rest of it. If you're looking at the 4th root of x and going, I don't know what the antiderivative is, you might help yourself if you rewrite that using rational exponents. Rewrite it as x to some power.
Oh, thank you. Yeah. Oh, yeah. Yeah. For a second, I thought we were 3 to 1. You don't feel like taking notes all the way or whatever.
We took a nerve out to help you. It's not
Good God. Good luck with it. Okay. You don't need to generalize over there. We find areas we definitely switch it from chords. Oh, okay, yeah. So it's more of an anti. Okay.
Divided by 5/4 is the same as multiplying by.
Oh, okay. Yeah,
Should be
I like,
16
I
over
went
5.
through basics, I'm like, wait, did I count too many
Yeah.
hours?
So let's play the same game that we did just a minute ago, and that is let's find the area of one rectangle. So area of one rectangle. And I'm going to be kind of consistent with this throughout section 5.4, 5.5, 6.1, and 6.2, that we're going to regard these little slices as being areas and then just add up all the relevant areas. So the area of one rectangle is going to be this distance here, which is dy, times this height here, which is going to be, in terms of y, let's see. Oh, you know what? We got a little problem here. I didn't think about this before I gave it to you. Because we're taking a dy slice, we should also do this distance has to be in terms of y. So yeah, my bad. Probably should have given you a heads up on that. So let's solve this for x. That will have x in terms of y. So I'll divide everything by 4. Yeah, we're hearing some thunder here because the math gods are mad at me. How would you get x by itself? What do you need to do? You need to raise both sides to the 4th power. So you're going to get y over 4 to the 4th power equals x. All right, so my bad. The area of one rectangle is then going to be dy times this expression where we've solved for x. So at a particular value of x, its height in terms of y is going to be y to the 4th over 4. So area of one rectangle is going to be, let's do it, y to the 4th over 256 times dy. All right. Let's finish this up over here. Example F. Now that's the area of one rectangle. Now I can move that rectangle anywhere I want, up and down, and then find the area by putting in the appropriate limits for my integral. So let's do that. The integral of 1 over 256 y to the 4th dy. What are the appropriate limits for this particular problem? Well, what's the smallest that I can take? Well, smallest slice I can take here? How far down could I move this little orange bar? Yeah, down to 0. So 0 here and 4 here, those are going to be my limits. 0 and 4. So looking good there. Let's find the antiderivative of y to the 5th. It's going to be 1 over 256. Excuse me, I said y to the 5th. Again, I'm thinking ahead. That's going to be y to the 5th over 5 between 0 and 4. Notice that you don't need a constant when you're trying to find an antiderivative here, because if you did put in a constant, it would subtract out. So let's see, this is going to equal 1 over what? That's 1280. 1280 times y to the 5th between 0 and 4. 1 over 1280 times 4 to the 5th minus 0 to the 5th. It's going to be 1024 divided by 1280.
Is there something written to the right of y to the 5th? I can't see.
It's just the
just-
one.
Thank you.
Thank you. All right, looking good there. Let's approach this a different way. just for, you know, the practice and to try and get a little perspective on some of this stuff. Now, because, let's see, you know what? No, it's not going to work out. Yeah. Maybe in section 6.1, we can try and find the area by taking a dx slice. If you took a dx slice, then things are going to change a little bit. I'd probably do this a fair amount different if I did a dx slice. You can find the area by integrating with respect to x. It's just going to change a few things. So, for now, we'll just stick with what we've got here. You know what, though? One thing we could do, let's do this. We could find this area by finding the area of the rectangle. So this thing here. But then we got to subtract off a piece, right? What do we got to subtract off from the area of this rectangle to get this little piece? I got to subtract off this area, right? And that'll leave me with this area. So let's see if we can't find the area underneath here and then subtract it off from, well, I guess it's a square, right? No, it is a rectangle. 0 to 1, up to 4. So the area of the rectangle minus this area, and let's find that area with a little rectangle like we did earlier. And let me do it this way. Let's take a little slice here. And the thickness of that slice is dx. What's the height of this thing? Yeah, not quite 4.
Oh, sorry, from.
Yeah, it's going to be 4 times the 4th root of x. So the area of one rectangle is going to be 4 times the 4th root of x dx. That's the area of one rectangle. Okay. So this is example G here. Let's find the area of this little piece right here. So that's going to be the integral of 4 times the 4th root of x dx. What are the limits going to be for this particular problem? Where could this slice be taken from? I think somebody said it here.
0 to 1.
Yeah, 0 to 1. So 0 is the farthest left you can go with these slices, and 1 is the farthest to the right. So that's going to be our limits. 0 to 1, 4 times the 4th root of x. Sometimes people take the constant and just write it outside. And the integral of x to the 1/4 dx, like that. Okay, not so bad. The antiderivative of that is going to be x to the 5/4. So let's put that in here, 5/4. Divided by that same exponent, 5/4, between 0 and 1. It might be in your best interest to clean that up. Dividing by 5/4 is like multiplying by 4 over 5. So I'll get 16 over 5 times x to the 5/4 between 0 and 1. That constant's just a constant, so I'm just going to leave it kind of factored out. 16 over 5 times 1 to the 5/4 minus 0 to the 5/4 1 and a 0. It's just going to give you 1 inside the parentheses, so 16/5 overall. But that's this area. If I want the area overall, I need to subtract that 16/5 from the area of the rectangle to find the area overall. Let's move over to another sheet.
So for an area, do we only find that through dx, or were we also finding that through dy?
We're actually going to find this area two different ways. We're finding it through dx and dy. We're not finding this area directly with dx. We're finding it indirectly, because what we need to do to finish this up is subtract off. So the area of the rectangle was 4, right? 1 times 4 for the height. Minus the area underneath the curve. Underneath and the curve. So that's minus 16/5. So it's going to be 4 minus 16/5. So that's going to be 20/5 minus 16/5 is going to be 4/5. And for a second, you might be worried. It's like, well, wait a minute, Mr. Parent. Those aren't equal. But yes, they are. If you put that in lowest terms, you'll get 4/5. So you're getting the same answer either way, which is a good thing. So that one and this one match. All right, so we found that area two different ways. We found it by integrating with respect to y, which worked out pretty nice once we realized we need to write this in terms of y. And then we integrated with respect to x and found it by subtraction. So two different ways, same answer. Let's flip over to the back side and keep working with a couple more examples there. Example H is kind of an interesting one. And again, you're running into a problem when you're integrating these things that we don't necessarily have a quotient rule for integrals. So let's see here. Example H. Integral from 0 to pi over 4 of 3 plus 7 cosine squared of x over cosine squared of x. You know what? This should be in a theta. It's all right. I'm just going to write it in terms of x. A little bit of a problem here. What are we going to do in order to finish this one up? How are we going to find an antiderivative for this stuff?
We
This,
have to move the cosine 2x.
You're gonna split up first.
split it up how, Ethan?
3 over cosine squared x plus 7 cosine squared x over cosine squared x.
All right. I like the looks of that initially. In particular because we get some simplification of our integrand right here, right? That's just a 7. So, all right, plus 7 here, dx. How about the first term? Is there anything I can do with that first term? Is there any way I can rewrite that one?
Cosine -2.
Holly? Yeah. So it's just going to be a 3. The reciprocal of the cosine is the secant, but we've got a cosine squared, so this is secant squared. Nice. That helps out a little bit. Who remembers the antiderivative of secant squared? just tangent. So 3 tangent of x plus 7x between 0 and pi over 4. 3 times the tangent of 7 over pi, or excuse me, pi over 4, plus 7 times pi over 4 minus the function at 0. And tangent of 0 and 7 times 0 are just going to be a 0. So I'm just going to put a big 0 in here. Pi over 4. What's the tangent of pi over 4? 1. If you don't remember that, just put your calculator in radian mode and take the tangent there. So let's see. Tangent of pi over 4 should be a nice even 1. Great. So we end up with 3 plus 7 pi over 4. And that's a nice exact answer. 3 plus 7 pi over 4. Do you want a reminder on how to do these things numerically on your calculator if you just wanted to check it? Your calculator's not going to be able to give you a nice answer like this, but it will give you a decimal answer. Want to review that? All right, let's just double check it. Now you have to be a little bit clever as you input this into your calculator. So let me clear out all my stuff here so you can kind of follow along. You're going to hit the math key. The 9th option down is for numerical integration. We're going to integrate between 0 and pi over 4. Now I know that the problem is written with theta, but we're going to do this with an x just for convenience. Now we got to be a little bit careful here. Let's put this in as it's written here. One thing I'll do to help myself out is do a fraction in kind of a nice fancy way. Instead of doing it with a little slant with the division key, if you hit the alpha key and then the y equals key, the first option here allows you to do a fraction. Just press enter. Now you got a nice horizontal fraction. You're not going to have to play around with parentheses as much. Hello. I guess the math gods don't want me teaching all these tricks. They're getting angry. So let's see. We got a 3 here plus 7 times cosine squared. Now you can't put the squared into the cosine, at least in previous operating systems. You can't put the squared there and have your calculator understand it. You have to be a little bit more clever. So we're going to take parenthesis cosine of x, 2 parentheses. The second one closes off the cosine, and that's where you can put your squared. We can practice that again in the denominator. Bless you. You're going to need more parentheses. Cosine of x, 2 parentheses, 1 to close off the argument, that is the x. The other one closes off the cosine. Now you can hit the square key. Finally, if you move over to the right far enough, you can put in the dx. See, your calculator insists on the dx, so do I. Wow. How do I know I got this right?
Plug in 3 plus 7 pi over.
There you go. 3 plus 7 pi divided by 4. And they look remarkably similar. So, feeling pretty good. Now, on an exam, typically speaking, I'll be asking for exact answers. If you want to check yourself this way, hey, that's great. If you don't, that's fine too. Whatever works for you. Let's see. Let's do example I. So we got an acceleration function. It's in meters per second squared. The initial velocity is given along the line. The initial velocity is 6. That's how fast it's moving at the start of this experiment. That's your initial velocity. So this function is for between times of 0 to 10. Find the velocity at time t. How would you find the velocity?
Well, T time is usually like, what, 8 a.m.?
Well, let's do it the other way. If I had the velocity, how would you find the acceleration?
Take the derivative.
Take the derivative, right? But if you have the acceleration, the opposite operation would be the antiderivative, which would be integration. So we want to integrate this. Integrate our a of t dt, and that's going to be our velocity function. Okay, so it's going to be the integral or the antiderivative of t plus 4 dt. Bob Real, what's the antiderivative of that going to be, please? T squared over 2 plus 4t plus anything? Plus c, plus our constant integration. But here's where the initial condition comes into play. The velocity at time 0 is 6. So v of 0 equals 6 would equal 0 squared over 2 plus 4 times 0 plus c, 0 and 0. What's that telling me about c? Yeah. This is 0, those disappear, you're just left with c equals 6. So your velocity function is just this. It's going to be v of t is 1/2 t squared plus 4t plus 6. Nice. Now if you want to find the distance that you travel in the interval from 0 to 10, then you're accumulating, you're adding up all these little distances. We did an example like that in section 5.1. We're going to do something similar to that here with this notation. If I want to find the total distance traveled, what do you think I'll do with this function?
You plug in 0 and 10. Average or distance?
Actually, you plug in 0 and 10. Those are the limits of your integral. And we're going to integrate this function, our velocity function, between 0 and 10 dt. Now, sometimes I allow you to get a little bit, let's say I allow a little economy of movement on exams. I don't want you to get these problems with polynomials wrong because you make a little mistake with some of the arithmetic. So for polynomials, sometimes I'll let you guys, and I'll tell you on the test, you can finish this with numerical integration. Sometimes I'll let you just finish it up with just that, numerical integration. So are we okay with the setup here?
Or when we were up at the top in the blue, the Newton S or whatever it's called.
The integral symbol, yes.
Yeah, the interval symbol. Do we not have to put anything for it there? Like we have 6 over 610.
No, that should be a 0.
Oh,
It's just
0, 10.
0 to 10.
For the BT at the top of the problem.
Here?
One more.
Oh,
Yeah.
here?
Yeah. We don't have to put anything on the interval notation there?
No. So what I did was I found the general function here. And then I went back and said, okay, this is the general function, but we happen to know that the initial velocity here was 6. So that's where we took and plugged in v of 0 was equal to 6. But v of 0 is also the same as plugging in 0 into this expression, and that's what allowed us to solve for 6 was equal to c. So that gave us the particular constant for our problem of 6.
Right.
So you plug in the 6 there, that's your velocity function.
So what is the interval notation when we were doing it be 0 to 6?
No, the c just happens to be your initial velocity. It doesn't
okay.
doesn't reflect the interval at all.
So the interval notation for when we were figuring out what C, the equation for C we don't have to put anything, one up there.
No, I just found the antiderivative there.
Got
Yeah.
it, cool.
Yep. Okay. So the integral function is kind of a way of accumulating things here. It's adding up, your little time slice times your velocity times time multiplied by velocity gives you distance. Now that distance that you're traveling changes with your velocity, and you can add up all those little changes to get the total distance traveled. So let's see what that total distance traveled is. And again, I'm going to use x as opposed to, let's see, I'm going to use x as opposed to the t that's written there, but it's still going to be the same. Integral between 0 and 10. Let's make it easy on myself. 0.5 x squared plus 4x plus 6. And then dx. I don't want to go there. Dx. And we'll hit the answer to fraction key just to make life a little bit nicer for your instructor. 1280 over 3. Okay. And that would be in units of meters. Nice. Okay. 2 more. And none of them are really going to require too much calculation on our part. First one is example J. If W prime is the rate of growth of a child in pounds per year, what does the integral from 6 to 8 of W prime of t dt represent? So a lot of choices here. I'll let you stew on that for a moment. You talk to your neighbors, see what you think. Were you guys just looking at that one?
No, example K.
Oh, we're going to do example K next.
I know, but it's so like minimalist of a.
It really is. But I didn't want to tip my hat at all.
Oh, sorry.
Yeah, that's all right. We'll get there.
Everybody loves the houseboat.
We're all the same.
But it also makes
But it makes sense.
because
It makes sense.
it's the derivative of the weight of the chunk.
So, is it like possible, like, to root for this thing?
I hate spoilers.
This wasn't an antiderivative. It's not an antiderivative. It's just rewriting it.
You just rewrote it, but, what I mean is, could you keep it like that, or do you?
Well, you could keep it like this, but I don't think you know enough to find the antiderivative like this. You're going to have to write it as something that you know the antiderivative of.
Because it would be too hard as a cosine of negative 2x.
Yeah, you just,
to take.
yeah, cosine of x to the negative 2, you're going to struggle integrating that as a cosine.
Oh, I see, okay, thank you.
Yeah. So what are our thoughts here? What's looking good? The change in the child's weight in pounds between the ages of 6 and 8. Is anyone liking that one? Yeah?
Yes.
Lots of nods there? All right, I'm liking your thinking there. The child's weight at birth? No. Child's weight at age 6 or 8? No. The change in the child's age? No, we're not talking about the change in the child's age. So, I mean, even without really understanding this too much, it feels like the first one's a winner. It is. What's happening here is that this is the change in weight times time, and those little things, those little increments are going to talk about, they're going to add up how much weight you're changing or gaining, assuming you're gaining weight in those years. So this one is our winner. All right.
I have a question.
Yes, please.
Is it possible to address it with this information and do something similar to what we did in example F to find the child's age? If we want to find the child's age indirectly, could we use this formula given the child's weight and time and age?
use that formula indirectly. I think you'd have to have the number here, and then you could probably solve backwards, like you're suggesting. So if you knew what this change in weight was, then I think you might be able to eventually work backwards. You know, find the antiderivative here. I think you might be able to work backwards and find the weight, but it would take a little bit of work.
Wouldn't it be the T, derivative of T?
Let's see. So if you had T prime, yeah, that would. I think you could. I'd have to think a bit more about that one. So, let me try and draw a little picture here to try and help out with your intuition here. So, suppose you have some function between 6 and 8, and it's the change, the rate at which somebody's weight is changing. So maybe at age 6, all of a sudden they put on a little growth spurt, slows down around age 7 or so. Let's just draw a little slice here.
Slow down. I was like, did they get shorter?
They would actually be losing a little weight there. So this is your time. This is the weight. So this little piece right here, that's a little slice called, we'll call it dt. And then, of course, we've got y equals w prime of t here. And that's the change in weight. So if you take the change in weight, multiply by a little time interval, that's how much weight change you're going to experience in that little time interval. Now, if it's, yeah, I guess you are still putting on weight here because this is a positive function. So it's just going to be how much weight did you put on in this time interval. It's just going to be the area of that. When you integrate, you're adding up all these areas. You're going to get the accumulated weight change in the interval 6 to 8. How much weight did you change, or basically, in this case, add on in those intervening years? So the integral function like this does often accumulate things. So for instance, if I had a function that talked about the rate at which I was paying interest back on a loan, if I was to integrate that, then I'd end up with the total money that I pay back on the loan, the total amount of interest that I pay on that loan. All right, last one. A houseboat. So let's see if we can't make a houseboat. And let me remind you of this thing right at the start. So reminder. What do I get when I integrate 1 over x? Yeah, ln of x. Plus that c. Let's not forget about the c. But instead of integrating something mundane like this, you could integrate other things like 1 over y, dy would be kind of similar, ln of y plus c. And technically, I think I should be putting in absolute values there. I'm just not really good at doing that. But let's do something a little bit fun. Let's integrate 1 over cabin d cabin. Any guesses as to what that was going to be? Yeah, ln of cabin plus c. Log cabin plus the ocean plus c. There's your houseboat. Yay! Get up, get a dog. Oh, come on, man. I have to wait an entire semester for one little math joke. Give me a little love on that one. All right, Antonio, you can't clap too well, so all right, the one-handed clap I'll accept there. But there you go. Houseboat. All right. Sorry if that was a bit anticlimactic, but enjoy.